Welcome to Math with Professor V. In this video, we're going to go over how to find absolute extrema for functions of more than one variable. And this is a continuation video, so I'll link the part 1 video lecture on this topic in the description, but I had requests from my Calc 3 students to do more examples basically. So I'm just going to summarize the process briefly and then work through 3 additional examples. When you're asked to find absolute max and min values of a function on a closed bounded set, so you have to be given the set, the first thing you do is you find your critical points that are inside the region on the interior, and this is the same way that we always find critical points. The second thing that you do is you find critical points along the boundary. I'll show you how to do that. And then the last thing is you find critical points from the corner points, and corner points are where the boundaries meet. And it can be a little confusing because these corner points need not look like a corner, like a sharp corner. So I'll show you an example where we're dealing with the circle. So just remember, corner points are where your boundary equations meet, okay? Then once you've collected all your critical points, you're gonna evaluate the function at those points, and then the largest function value is the absolute max and the smallest is the absolute min. Okay, I apologize for my voice too. Professor V was out partying this weekend, so I lost my voice a wee bit, and I don't know when it's coming back, and I had to get this video out. So here we go. Find the absolute max and min values of f on the set D. So here's our function. I recommend always graph D. That way you can easily identify all your boundaries and your corners. So x is between 0 and 2 inclusive. Y is between 0 and 3 inclusive. So we've just got the loveliest little rectangle you ever did see. Here we go. Y and x. And y is going all the way to 3. Okay, 1, 2, 3. And x is just between 0 and 2. Okay. So here's our region D. Let me shade it in. Other thing to keep in mind too is, like in part 1, when we're finding critical points on the interior, make sure they actually lie within this region. If any of them are outside, you just throw them out. Okay, so step 1, we're going to find critical points on the interior. So this is the same way you find just critical points in general. Partial with respect to x, that'll be 2x minus 2. And then we set that equal to 0, and we get x is equal to 1. Repeat, partial with respect to y, that would be 4y minus 4. I set that equal to 0, and I get y is 1. So both my partial derivatives equal 0 if x is 1 and y is 1. And is that point on the interior of my region D? Well, yeah, 1's like right here. So we're good. We'll keep that guy. Meaning we're going to hang on to it and evaluate the function at that point later. Okay, next step, I need to find critical points from all the boundaries. Oh, how many boundaries are there? There's 4. There are 4. There's y equals 3 up top here. There's x equals 0, y equals 0, and x equals 2. So what do? One at a time. Let's start with, say, y equals 3. I'll label what's going on. You're going to substitute 3 for y into the original function right here. And you're going to make it a function of just one variable. So I'm going to have f of x comma 3. So this is going to be x squared plus 2 times 3 squared minus 2x minus 4 times 3 plus 1. Now, clean up. So this will be x squared minus 2x. That's 18 minus 12 plus 1, so 7. Good. Now, this is a function of one variable. I want to find critical points that are on this boundary right here. So now you're basically back in Calc 1 when life was relaxing and you didn't realize that you were probably stressed. So you're going to take the derivative, but it's just f prime now, right? It's not a partial derivative. And that'll be 2x minus 2. Again, we set this equal to 0, and I get that x is equal to 1. But I got that x was equal to 1 provided we were on the boundary y equals 3. So that's the y value or the y coordinate that goes with x equals 1. So 1, 3 is a critical point on the boundary. And you can tell indeed, yep, it's on the boundary. So it's not in the interior. 1, 3 is like right here on this boundary line. So save that for later. Save for later, save for later. Okay, moving on. You just got to repeat. So I did y equals 3. Now I'll move and do x equals 0. So again, you go to the original function right here. And I'm going to substitute in 0 for x. So we have f of 0y, that's going to be 2y squared minus 4y plus 1. Okay, so f prime is going to be 4y minus 4. Again, we set this equal to 0, and I get that y is equal to 1. Well, getting y equals 1 comes from assuming we were on the boundary where x is 0, and 0, 1, you could see it's right there. So it's on this boundary. Perfect. Okay, 2 more times, right? We have 2 more boundaries. Let's move on to y equals 0 next. Oh, I need a page. I need a page. You guys got the picture, right? Because I'm just going to scroll down since there's a page break and it's offending me. Okay, y equals 0. So we'll have f of x comma 0, which is going to be x squared minus 2x plus 1. And then f prime is 2x minus 2. Set that equal to 0, and you get x is 1. So we have 1 comma 0 from that boundary equation. And then the last one is x equals 2. So then we have f of 2 comma y. So that would be 4 plus 2y squared minus 4 minus 4y plus 1, which simplifies to 2y squared minus 4y plus 1. So then f prime is going to be 4y minus 4. Set this equal to 0. I get y is equal to 1. That came from being on the boundary that x is 2. So 2, 1 is another point. Okay, so I have 1 critical point from the interior, this one. I have 4 from the boundary, 4 that are like on the actual boundary. And then what did step 3 say? Find the critical points from the corner points where the boundaries meet. So I'm going to have 4 of them. 1, 2, 3, 4. Now in this case, they actually look like corners of a room or whatever. But the definition is that it's where one boundary equation connects to another boundary equation. That's considered a corner. So let's just list them out. So step 3, make sure that way you know you've collected everything. So your corners are where? They're at 0, 0, 2, 0, 2, 3, and 0, 3. And sometimes like things will be duplicated. They'll come up again, but in this case, no, right? Everything so far is distinct. Okay, now, yes, you have to sit there and evaluate the function at all of these. I'm so sorry. So here we go. F of 1, 1, f of 1, 3, f of 1, 0, f of 0, 1, f of, I lost where I was, f of 2, 1, f of 0, 0, f of 0, 3, f of 2, 3, and then f of 2, 0. Okay. And this is how we determine, you know. So you will not do the d-test for these problems. Nobody cares if it's a local min or max. The directions are asking for absolute extrema, so don't compute d. No one asked you to. Okay, this is -2, 6, 0, -1, -1, 1, 7, 7, 1. So boom, here are my absolute maxes. And right here at f of 1, 1 is my absolute min. So notice in this case, 1, 1, that came from the critical point on the interior. That gave me my absolute min. And then these were corners, weren't they? The absolute maxes. Yes. Okay. So if you think about it, it should make sense because, look. What is this the graph of? This is a paraboloid basically, right? Shifted. And we know that it would have an absolute min naturally, but not an absolute max, only if we restrict the domain. So that's why the absolute max occurs exactly at the corners, right? Okay, I say graph it if you want. You know what? Let me just do it. So you can see here, right, that on the rectangle that we were given, if I look here, we were restricted from x being between 0 and 2 and y between 0 and 3. So naturally, the absolute min does occur within that region, right? That's why that one came from an interior critical point. But obviously, like this function here, it doesn't have an absolute max naturally, right, on its original domain. If we restrict the domain the way we did to that rectangular region, then yes, of course, it will achieve an absolute max at the corner. That's when it's going to be the largest. So you can always graph to confirm, you know, and it's good to intuitively understand what's going on. All right, next example, we have f of xy equals 2x cubed plus y to the fourth. Our domain D is everything on and inside the unit circle. I'm going to graph it. You might be like, Professor V, I know what a circle looks like. Yeah, but you know what? You really need to identify the boundary equations clearly. And you know what else? This one's tricky to figure out the corners unless you're thinking carefully. So we're graphing it, okay? Here's x, here's y. This is 1, 0, as you know, 0, 1. Alrighty, so first let's start off, let's do the relaxing part. Let's get critical points that are on the interior. So partial with respect to x, that would be 6x squared. Set it equal to 0, I get x is 0. And then very similar, partial with respect to y, 4y cubed. Set it equal to 0, I get y is 0. So these are both 0 if we're at 0, 0. Is that on the interior of my region? You know, I didn't shade it. Shame on me. Here we go. Yes, 0, 0 falls within my domain D. Okay, perfect. So there's one critical point. Next, we have to look at critical points on the boundary. So the best way to proceed, that way you don't miss any points, any corner points, is that you isolate one of the variables, either x or y. It doesn't matter which. So my actual boundary equation is x squared plus y squared equals 1. I'm going to isolate y. So y squared equals 1 minus x squared, which means y equals plus or minus square root 1 minus x squared. So technically, I have two curves that bound this region. Boundary number 1 is y equals positive square root 1 minus x squared. And boundary number 2 is y equals negative square root 1 minus x squared. Okay? The reason I'm doing it this way is because notice boundary 1 would cover the top half of the circle. Boundary 2 would cover the bottom half of the circle. And I'm going to do it a little bit out of order. I'm going to jump straight to 3 and say, let's find the corners. And the corners are defined as points where one boundary equation connects to another. Well, the way I've defined it, that I have a top half of a circle and a bottom half of a circle, means that these boundaries meet at 1, 0 and at negative 1, 0. Very good. Negative 1, 0 and 1, 0. Now, technically, you didn't need to isolate y to find critical points that are on the boundary because we have this y to the fourth. So you could have played around with it a little bit. But if you didn't explicitly solve for y this way and identify top boundary equation, bottom boundary equation, you would have a difficult time identifying that those were the corners. So that's why I teach it this way. That way you don't miss any important points, okay? Very good. Now let's proceed with finding critical points on the boundary. So f of x, and then since I am noticing y is to an even power, I can just combine both cases here. It won't make a difference if I have positive or negative. Do you know what I mean? Yes, Professor V, we know what you mean. Oh, good. Okay. So this is going to be 2x cubed plus y squared squared. Yes? 1 minus x squared squared. Beautiful. So 2x cubed plus 1 minus 2x squared plus x to the fourth. Okay, derivative. So f prime is 6x squared minus 4x plus 4x cubed. And then we're going to set this equal to 0. Ooh, okay, we can factor out 2x. Let me put the rest in descending powers. Then it's 2x squared plus 3x minus 2. And then the 2x, leave it out. This factors, right? This is 2x minus 1 times x plus 2. So then we get x is 0, or x is a half, or x is negative 2. Well, x can't be negative 2. That's out of bounds. Get out of here. If x is 0, then what would y be? Well, remember, we're on the boundary. So y is plus or minus square root 1 minus x squared. So it would be plus or minus 1. And then if x is a half, y would be plus or minus, we're on the unit circle, guys, we're at 3 over 2. Okay, so technically I have 4 points here from the boundary. I have 1 from the interior and 2 corners. And I know they don't look like sharp corners. I was set in the corner often as a child. I don't know, like as punishment. Get in the corner. Nothing was worse to me than not being able to do something. So having to stand in the corner was like the ultimate punishment. I don't know tell me if you were sent in the corner. Anyways, that's it. So we got to evaluate the function at all of these points. Have no fear, I did it for you. So f of 0, 0 is 0. F of 0 plus or minus 1 is 1. F of 1/2 plus or minus, we're at 3 over 2 is 13 over 16. And then f of negative 1, 0 is negative 2. And f of 1, 0 is positive 2. Oh my goodness, the corners. It was all about the corners. And had you not been able to identify them, you would not have gotten the correct answer. So there's our absolute min, and I don't know what I was attempting to do there, guys. That's the absolute max. Good? Okay, I have one more. It is spicy. You know, it's not hard. It's just, I promised them I would do a new one in the video. So here you go. Here you go, my angelic class. F of xy equals x cubed minus 3x minus y cubed plus 12y. And then D is the quadrilateral whose vertices are negative 2, 3, 2, 3, 2, 2, negative 2, negative 2. Okay, let's graph this guy. And that's it. X, Y. Okay. 1, 2, 3. I'm just going to go, yeah, we need kind of stuff everywhere, don't we? 1, 2, 3. Okay. So the vertices are where? Negative 2, 3. 2, 3. How lovely. 2, 2. Oh, so close. And negative 2, negative 2. All the way down here. All right. So here's our quadrilateral. Lovely. And then this will come straight through like this. Okay, perfect. So let's go ahead. Let's find critical points on the interior first. So on the interior, proceed as normal. Partial with respect to x, 3x squared minus 3. Set it equal to 0. X is plus or minus 1. Okay. Partial with respect to y, negative 3y squared plus 12. Set that equal to 0. And then you get y is plus or minus 2. Okay, so we're going to make every possible pairing. Let's see. 1, 2, 1, negative 2, negative 1, 2, and negative 1, negative 2. But do you notice not all of these are within our region? 1, negative 2 is not. 1, negative 2 is over here. So throw that out. Who else can I throw out? Negative 1, negative 2, right? Okay, so only these two are in the region. Very good. Now we have to do the boundaries. How many are there? 4, yes. Oh my goodness. Okay. So let's list what equations we have. Up here, this is y equals 3. This is x equals -2. Oh, this is just y equals x. And this is x equals +2. Okay, so you have to do the process 4 times for the boundaries. So I'll start off with, let's do y equals 3. So f of x comma 3 is going to be x cubed minus 3x minus 27 plus 36. Whatever, I'm just going to take the derivative now. F prime is 3x squared minus 3. Set that equal to 0, and you get x is, yep, plus or minus 1. So we have 1, 3, -1, 3. Make sure those are, yep, that's on that boundary line. That's on that boundary line. Okay, save these. We're going to have to test them in the function. And then keep going, keep going. Let me put like a divider. Yes, that looks better. Okay, let me test on y equals x. You'd have f of x. So it's x cubed minus 3x minus x cubed plus 12x, which gives me 9x. So then f prime is 9, which doesn't equal 0. Okay, what does that mean? That means there's no critical points on this boundary line. Fine with me. Less for me to test. Okay, next one. Let's do x is -2. So f of -2y would be -8 plus 24 minus y cubed plus 12y. So f prime is going to be -3y squared plus 12. Set that equal to 0. So y is plus or minus 2. And that came from assuming x is -2. So we've got -2, 2, -2, -2. Are those both on there? -2, 2, -2, -2. That's actually a corner, but whatever, that's fine. Okay. Sure, you guys are good to go. And then one more. X equals +2. X equals +2. Then you have f of 2 comma y. So 8 minus 6 minus y cubed plus 12y. F prime is -3y squared plus 12. Set it to 0. Y is plus or minus 2. And then, yeah, I think 2, 2, and 2, -2. Now let's check both these. 2, 2, 2, -2. 2, 2 is actually a corner. 2, -2 is outside the region. So throw that one away. This is the only critical point that's actually on the boundary. And then last thing, we need to list our corners. So you can go look at your picture here. -2, 3. -2, -2. I actually already had it right here. Okay, so I'm only highlighting the fresh new ones. And then we have 2, 3. That one's new. I don't think we got that one yet. 2, 3. And then who else? I'm missing somebody. -2, 3. -2. Oh, 2, 2. But we already have 2, 2. Okay, so we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 points to check. I did it for you already. Are you ready? Here they are. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can see absolute max. It can pop up more than once, no problem. Absolute max. Absolute max. And then absolute min is right here. Okay, so that concludes the video. Hope you found it helpful. Don't forget to give it a thumbs up, subscribe if you haven't already, and check out the rest of my Calculus 3 video lectures on the playlist Calc 3 video lectures. I know, so original. If you need more help, don't forget to follow me on Instagram and TikTok, MathWithProfessorV. I'll be back sooner than later, guys. Bye.